So the only problem is the manufacturing is a big problem here, because I'm going to show you some of the DRS uh, in the end of the this particular lecture. So why? Because you're going to use extensive glue. That glue is somewhat bit costlier. Without that glue, that glue's epsilon r value also you should consider in the simulation and also in measurement. If you consider in the simulation, you'll get accurate measurements in the while testing, while verification. Otherwise, if you're not using that glue's epsilon r also, you may not get accurate results. So that is another. Fabrication is a bit costlier and bit tedious, complex. But nowadays, with the current technology, with current development in the machining technology, you can do very easy, right? Earlier days, in the 10 years back or 15 years back, it was a bit tough. Now it is very easy, right? Coming into the circularly polarized dielectric antennas. The concept is same as a patch antenna. I've taken two novel slots. Opposite slots are equal, and the time phase variation is going to bring the circular polarization. Next. So this is just a probe penetrated cylindrical DRA with four slots, where opposite slots are equal. Areas of volume of opposite slots are equal. Next. So this is field variation, because in dielectric material you cannot show that, because in the on the metallic antennas you can show surface current, but coming to the ceramic material you have to show the field variation, whether it is giving circular polarization or not. So here wide bandwidth has been achieved from almost 4 gigahertz to around 7.5 gigahertz, and also wide axial ratio bandwidth has been achieved with this particular design. And next. So another thing is in order to achieve this particular wide bandwidth and wide axial ratio, the excitation is very important. Excitation, if you're having slots across the axis, I mean x-axis and y-axis, you have to come across. Feeding should be in the diagonal in nature. So you have to variate. I mean, you have to do the parametric study across the diagonal, so that in order to achieve wide impedance bandwidth and wide axial ratio bandwidth, that is very important. That you have to do through parametric study or optometrics. Optometrics is available in all the HFSS and also CST Studio, right? Next. So these are different variations. As I told you, there is a degree of freedom for diameter of the dielectric, and also the probe height is also plays important role. Where exactly you're getting more bandwidth, that has been taken. Next. So this antenna is also I've tested for scale down approach. That means that initially the antenna is bigger in size. It is around 40 mm by 40 mm. Now it was been tested for 20 mm by 20 mm also. That is why you can see the axial ratio is given for there for scaled down version. I could not able to get the more wide axial ratio bandwidth, but parts of it I've got it, right. So this is scaled down version. See, earlier the antenna is operating in 4 to 7.5. Now the scaled down version is operating in from 8.8 to around 13.5 gigahertz, right. Next. So these are two antennas, SDRA1 and SDRA2, slotted dielectric resonator antenna 1 and slotted dielectric resonator antenna 2. So this particular antenna is tested in anechoic chamber, and the results are verified. Next. So you can observe the glue. See, glue was displaced across the surface. That is why my results are a bit variant in the end. So the glue plays a very important role. Next. So that is why, see, second one, SDRA2, the retinal loss was big sketchy, right? So but the SDRA1 is good, because of the displacement has happened because of that particular glue, right? So because of that, it is a bit sketchy, right? Next. And all the radiation patterns wherever I have taken, because as I told you, the XZ plane and YZ plane, both the planes should be equal. Then only you get axial ratio below 3 dB, because there is should be difference should be on x plane and yz plane should be very less. So then you're going to get it get the small difference. Then the axial ratio will be good, right? Next. So this is the first one is giving wide axial ratio bandwidth, but second one is a bit changed. It is giving only at particular frequencies like 8 and 11.5, right? Next. And the gain is constant across the bandwidth. It's around 5 to 6 dBi, and for the SDR2 it is more than 5 to 5.5. Its maximum is 5.5. It's a constant across the bandwidth. Next. So this is also compared with the earlier designs, and this is the gain is good, and the bandwidth is also good when compared to the compared version, compared literature at that particular point of time. Right. Next, this work is also published in IEEE Antennas and Propagation magazine. This is another work. Right. Next. And another, up to now we have seen wideband antennas. Now I've done some novelty in the trying to bring the novelty in the aperture configuration. So aperture coupling DRS I've done 2 or 3 versions. So these L slots, coupled L slots and parasitically coupled L slots, 2 configurations of L slots I have used, and those L slots current distribution I have measured. So because if you remove the DRA, it acts as a slot antenna, right? Aperture antenna. So if you place a DRA, it is aperture coupled DRA. It is going to become an aperture coupled DRA. So first I have tested for slot antenna, then I mounted DRA on top of it, right? Next. So this is what I'm talking about. First, A1 and A2 are two different coupled L slots I've used, and A3 and A4 are two different parasitically coupled L slots. So here you can see one L is bit longer when compared to another L. So that itself is going to bring two orthogonal modes, right? So that is the technique that I have generated in order to get the CP radiation. So this is the novelty in this particular form, right? Next. So see, you can observe the 2 proposed antennas. See, at 0 degrees, the field is rotated on the top L slot in the top figure, and it is rotating. You can observe it is transforming. It is giving the surface current to the next L slot in the 90 degrees, and then 135 degrees it is going back again. That means that it is rotating left hand side. So it is LHCP radiation. And if you see in the second antenna, bottom L slot is excited, and it is transforming towards top L slot, and then it is rotating, and it is giving you CP radiation, right? Next. So on the top of it, I have placed the DRA. Small length of DRA is 10 mm, small 10 mm height of 5 mm. I think it's 5 mm height of DRA. I placed on the top of it, and I tried to exploit what this particular DRA is going to do when you place on these novel kind of slots. Next. So this is tested in anechoic chamber again, and then next. So the S11 is compared, and see, you can observe one is a linearly polarized band, another one is 2 orthogonal modes are generated, that is giving CP radiation. And coming to DRA3, DRA3, you can see 2 CP bands and 1 LP band, linearly polarized band. So first one is 1 CP band and 2 LP bands, and second one is giving 2 CP bands and 1 LP band, right? The corresponding axial ratios are plotted in the next slide. Yeah, shown in next slide. So, and the corresponding radiation patterns of this particular DRA2 configuration, and next DRA3 configuration, and next. So the corresponding axial ratios, wherever you are getting CP, there only you are going to get axial ratio, right? Next. So the gain, see, the multiband antenna gain is not constant, right? Whenever there is no radiation, there is no gain, right? So if you see at 5 gigahertz, there is a gain of around 4.5. But at again at the multiband at 8 gigahertz, there is a gain of around 6. And then at 10 gigahertz, its gain is more. Similarly, the same for the second design also, right? Next. So this work is also compared with different aperture coupled antennas. Here, number of CP bands are less in the earlier designs, but here I've got three. Initially, I've got one design, I got three, and whenever those two L slots are same, when the L slots are different to each other, coupled L slots, you are getting 3 and 1 CP. And whenever there are parasitically coupled L slot with different dimensions, not same dimensions, then I'm getting 4 out of 4, 2 CP bands and 2 LP bands, right?